Muted. Okay. Can you hear me now? Can the people in Zoom hear me? I know David. David, you are both in Zoom and here. So can you hear me in Zoom? Because no one in Zoom is replying to me, but I think I can be heard. Oh, okay, good, good. So there exist people who can hear me in Zoom. All right. One more minute. So we have a very healthy audience here. So you all know about the homework, right? The number of problems is 10. It may sound a little bit too many, but each of the problems is very bite-sized in the sense that I don't think it will take you long to do each of the problems. So I suggest you get started as soon as possible, but I don't think it will take too much time if you understand the core concepts. Many of the questions are very similar to the examples that I do. Okay, so without further ado, let me get started, assuming the people in Zoom can hear me. All right, so today we will go through sections 1.5 and 1.6 on independence and on counting. All right, this is on independence, this is on counting. You have to read all these sections. That's the homework. Now, before I go through that, because independence here requires us to know a lot about the total probability theorem and Bayes' rule, this is where we left off last time. So I want to go through it slowly one more time and supply another example. As usual, in probability, we start off with a sample space that is the set of all possible outcomes. All right. And events are subsets of the sample space. So if I have a bunch of subsets, i.e. events, that are disjoint, what is the meaning of disjoint? That means they have nothing in common. All right. The intersection is empty. All right. That form a partition. What is the meaning of partition? Partition means you take the union of everything. You don't leave out any elements of the sample space. So here's a picture of a partition, A1, A2, A3, A4. They are disjoint, and you take their union, you get this rectangle, which is the sample space, okay? So we assume that we are not in a degenerate scenario, but we assume that all the events in the partition, they have probability, at least their probability is greater than 0. Then what we have is the following. This is called the total probability theorem. Okay, maybe we'll put it in red because it's so important. Total probability theorem, or law of total probability, some people say. Okay, but we follow the book. All right. So P or B, suppose I'm interested to evaluate the probability of some event B. Okay, then I can basically split this difficult problem into small sub-problems of considering the probability of B and A1, B and A2, ... up to B and AN, okay? But each one of these, if you remember, each one of these guys is nothing but the conditional multiplied by the marginal. So this is a formula you have to commit to memory. And here we are applying this formula n times, all right? So we know that the conditional probability is the joint or the intersection divided by what you condition on. Okay, so that is just nothing but applying the formula n times. That is the total probability theorem, and we will use it. We also mentioned last time Bayes' rule, which you should commit to memory. Now, Bayes' rule says, okay, suppose you know that a particular event has happened, B has happened. What is the chance that A has happened? AI, okay, one of the events in this partition. You know that you are living here. What is the chance that you are also living in A1? Well, that's a small chance here. Okay, but let's quantify that. Well, just by using the definition of conditional probability, you get that this is the joint divided by what you condition on. Then you can flip this around to write this as, well, this is the conditional, this is what you condition on, all right? So that gives you the joint here, right? So I'm not touching the top here, not touching, I'm touching the bottom. What am I using for the bottom? What am I using for the denominator? I'm using exactly this total probability theorem in green, putting down here. So we are not cheating, okay? Now, whenever I write all this 1, 2, 3, dot, 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 all the way up to n, it's very, very laborious. So we can actually use the summation symbol to add everything up together. And in case you have forgotten, so the summation of, say, a bunch of numbers, ai, I running from 1 to n is a1 plus a2 plus dot, dot, dot plus an. So this is some basic math symbol. Now, then we can also consider the product. Okay, this is the product symbol. It's very much like the sum symbol, except you multiply the n numbers together. Okay, right, this is just a recap of these standard symbols that we will use, right? All right, so these are the two theorems that we have to commit to memory. But beyond committing to memory, this class does not require you to prove anything, okay? This class requires you to know how to use the theorems in an intelligent fashion when you are faced with some problems, okay? So now, here, every time as you know me, I will illustrate theorems with examples. We play now in a chess tournament, and we just play one game. We are not playing multiple games. And we have three possible opponents. Okay, event AI is the event that we get opponent I. And there are only three possible opponents. Okay, John, is it John? No, sorry, David, you know, there, Oliver, and these are the only two names I know. So Vincent, no, but I cannot play myself. Okay, so I only know two names now. But B is the event that I win. Now, if you get a weak player, the chance that you win will be higher. Okay, and here are some representative numbers. So suppose I play with this very strong player, I may win or lose with equal probability. But these two players, A2 and A3, they are weaker players, and you have a very high chance of these are the chances, the probabilities that you get an opponent I. Okay, so this is the chance that I play with Oliver. Oliver is player 1. Okay, and these are the chances I play with the two other players. And of course, these must add up to 1. And you cannot play with two players at the same time. So these events are disjoint. And you notice that if you add up all these probabilities, you get 1. So this is a partition of the sample space as required. Now, if you play with player 1, you win with probability 0.3. Wow, Oliver is a great player because I only win 30% of the time. Here I win 40% of the time. And here I win again 50% of the time. Okay, so these are just some random numbers. So now the question is, okay, now if you look at this, suppose I play with Oliver, I win 30% of the time. This is one way of posing or stating uncertainty. But this is another way of stating uncertainty. Suppose now I win. So i.e. B holds, event B holds. That means I won. What is the probability that I played with, say, Oliver? Okay, with opponent 1. So now we are going backwards. This is going backwards, right? Because we have all the forward information. The forward information, I play with Oliver, I win 30% of the time. I play with David, I win 40% of the time, and so on and so forth. These are the, think of it as a forward direction. But now we are interested in this particular probability. A1, that means I played against Oliver, condition on the fact that I won. Can you see that? This Oliver, condition on the fact that I won. That means I'm living in the universe that I won. All right, what is the chance that I play against a certain player, A1? Now, you see that this is going to be very different from this. All right, these are completely different things. Here, I know I'm playing with Oliver. What's the chance that I win? Here, I won. What's the chance that I was playing with Oliver? Is this absolutely clear? Absolutely clear. Very important. Okay, the direction matters. The direction matters. And okay, now let us do an exercise here in the middle of an exercise. This is very bad teaching. Okay, what is this? Can you give me a number? Zoom people. Suppose I play with Oliver, what is the chance of B complement? Okay, that's one try. Any other tries? Yes, better, 0.7. Because these two have to add up to 1. These two have to add up to 1. Okay, have to add up to 1. Because you are conditioning on the same thing. So I'm playing the same person. I either win or lose. There's no draw. Okay, so now please note that if you are conditioning on the same thing, B and B complement must add up to 1, because I got a few questions, I think last time or the time before. Okay, so now, all right, please remember this. Okay, very, very important. So now I'm just going to apply the above formula, okay, which is P of A1 times P of B given A1 and the sum. Okay, I'm just going to write J running from 1 to 3 of P of AJ, P of B given AJ. If you are not comfortable with this, you write out 3 terms in full. Okay, so now it's a matter of plugging numbers, right? Probability I pick Oliver is 0.5. Probability I win against Oliver is 0.3. Okay, and the bottom is nothing but 0.5 times 0.3. So I'm just taking the product here, and then I'm taking the product here plus 0.25 times 0.4 plus 0.25 times 0.5, which is, after you put it into the calculator, you get this number here. Okay, so as you can see, this is a very simple example, but we are flipping things around. All right, we know that we won. Who did we play with? This is a different question than if I played with Oliver, what is the chance that I win? Okay, now I just want to remark here that whenever we conditioned on, say, A1, we have probability B given A1 plus probability B complement given A1 is equal to 1. Now, very important, okay, of course this is true, but if you consider, say, probability of B given A plus probability of B given A complement, this is not 1 in general. Never. Okay, so let me emphasize this because last time people asked me this. This is really important. Now, what you condition on must stay the same. Here they stay the same. You are conditioning on staying the same. Then if you change the BBC, B and B complement in front, good for you, you add up to 1. Now, these two are not the same. One is this color and one is this color. Right? Not the same. Then there's nothing you can say. You can say nothing about it. Okay? All right, this is really important. Okay. And any questions on this example and on the 2 theorems that we covered last time? Bayes rule and total probability theorem. Any questions at all? So there are a few things you have to commit to memory. The total probability theorem and Bayes rule, you have to commit to memory. But as you commit yourself to memory, you also have to know how to use it in some simple scenarios like this. Can you see that? Okay, if I ask you a question, it will be, I won't trick you, okay? You need to know what numbers to plug in. And you need to know how to interpret those numbers properly to use the existing information. So for example, in some scenario, I may not be so kind. I may give you probability of you losing condition on A3. I may give you this number instead, this x. Then you must know that you have to flip this in order to plug it into the base rule total probability formula. Okay, so for this, you must get this. Okay, so you need to know how to think a few steps. Okay, I'm going to erase this. Okay. Any questions at all from the Zoom people? You can see me today, right? I position the camera. So this is just a recap from last time. I like to do a recap from last time. Any questions in the Zoom? Okay, so if not, I'm going to go through this, which is discussed extensively in section 1.5. But the section 1.5 is a little long. I will only talk about some issues there. And I have no time to talk about everything. I will just talk about the most important issues, okay? Recall that we have the conditional probability formula for any B that has positive probability. So that is A intersect B divided by PB. For every, this symbol here, this math symbol is called for all, right? But let me write it in English. For all events B with positive probability. Okay, this is just from before. Now, however, if in the situation that if, okay, B gives no information about A, all right, the two events are called independent. Two events, A and B, are called independent. Now, intuitively, you know of some events that are already independent. If you toss a coin, all right, and whatever it shows up, that outcome is independent of your friend tossing another coin. All right, they got nothing to do with each other. All right, so perhaps what are dependent events? Oh, whether or not you slept well last night and your performance in an exam. That's pretty dependent. You know, you need to sleep well in order to do well in an exam. All right, whether or not Oliver slept well before the night and how well I am teaching. All right, those are probably independent. Okay, so let us try to formalize this in terms of mathematics, some symbols. So there are some events that are independent and some events that are not independent, and we will do some calculations, simple calculations. So this is a definition independent, but more specifically, we say that mathematically, for two events in a sample space, for A, B, events in a sample space, we say that A is independent of B. And sometimes I will write A perpendicular to B like this. Okay, because writing A is independent of B requires a lot of English, right? A is independent of B if, all right, probability of A given B, and we know what this means, is equal to probability of A. All right, so that means knowledge of B, even if you know that you are in B, it doesn't influence your knowledge of A. Okay, so that is a mathematical definition. That again, there are not too many things that you commit to memory, but this definition you should commit to memory. Okay, this is a very important definition. Okay, but here are some consequences of the definition. So notice the following. Now, let us take this equation here, equation dagger, and multiply the probability of B, which is a positive number, or at least non-negative number, on both sides of this equation. Then what do we get? P of A given B times P of B equals to P of A, T of B. Now this is equivalent to probability of A intersect B. All right, this is equal to PA, PB. And this is a consequence of just using this formula here, the conditional probability formula. As you can see, the probability of the intersection is the product of these two guys. Okay, and so I've written the probability of these two guys is the probability of the intersection here. Okay, cool. right? Please let me know if I am going too fast or too slow, whatever. Okay, so the point here I want to make is that A and B being independent is equivalent to this equation here, which we can give a symbol dagger. Okay, so there are two ways of saying independent, either this or this yellow thing here. Okay, so they are the same thing. Now, in the above description, we say that A is independent of B if something happens. Now, do you think that if I teach very well and Oliver had a good sleep last night, they are independent if Oliver has a good sleep last night and I teach very well? So A independent of B, is it the same as B independent of A? Now let's have a proof that this is true. All right, you see, now starting from dagger, we see that. All right, so this is PB, P of A given B. Why is this so? Now we have probability of A intersect B is equal to this. All right, what is the meaning of conditional? Conditional means you take the joint or the probability of the intersection divided by what you are conditioning on. And what you're conditioning on is B. All right, so you can move this one down here and divide by PB and you get P of A given B. So this equation holds up. All right, you need to know this direction pretty well. Starting from this, you see this, and this is equal to P of A, P of B. And here, what we are using here is the dagger equation here. And this first equation here is nothing but using the definition of conditional probability. All right, now if PB is not 0, we can cancel this. Oh, I'm sorry, I don't mean to do that. Cancel this. And so what we are left with is the probability of A given B is equal to probability of, oh shucks, I didn't mean to do that. Probability, oh, I meant to do this, sorry. Okay, here what I meant to do is, I should really follow my notes. P of A, P of B given A. All right, and now whatever direction is fine. Now I can cancel PA. Okay, and what I'm left with is probability of B given A is equal to probability of A. And as you can see here from the definition, we say that A is independent of B if so. Hence, this relation says that if A is independent of B, then, okay, what we are saying here is that if A is independent of B, B is independent of A. Because the equations here swapped the A and the B. So this is very natural. If I'm independent of you, you are independent of me. Okay, it's very natural. But sometimes in higher mathematics or in some things like machine learning that you may learn, all right, if I cause you, you may not cause me, right? So causality is unidirectional. So if you smoke, then you will have lung cancer with high probability. But if you have lung cancer with high probability, it may not mean that you will smoke. All right. Well, so you can see that here A independent of B means B independent of A. Okay. And here is a short proof. All right. Okay. So we of course write this as A independent of B, like this. That's B independent of A. Yes. Yeah. Where's the typo? Yeah. Which line? This line? Oh, sorry. This line? This one? Oh, this should be PB, typo. Yeah, thank you very much. Yeah. So A does not influence B. That's the meaning of independence. Thank you very much. What's your name? Okay. Let's do an example. Okay. Now I do two successive rows of a four-sided dice. This example is not easy. Okay, it's a bit interesting. There are 16 equally likely outcomes. Some of the examples that we choose are easy, some of them are not. So the outcomes are indexed by I and j, they are 1/16 for any ij running from 1 to 4. So for every pair, the probability that you see that pair is 1/16. And here the order matters. Okay, so by this we mean the order matters. So because the first row, the second row, you know, they are identified by the first row being something and the second row being something. All right. So now let us define some events. Let's say AI is equal to the first row is I. And here I can take on 4 values, 1, 2, 3, 4. And B is BJ. BJ is second row is J. Here again, J can take on 4 values. Okay, so the first question is not so difficult. Are AI and BJ independent? All right, so here, obviously, you know that it's independent. Hopefully, you have the intuition that it's independent. But can we actually verify this formally? All right. Now, you know, okay, so let us consider P of AI intersect BJ. So this means that the outcome is IJ, which is exactly this guy here. So that's 1/16. All right, that is 1/16. I'm writing it in 2 different ways. This is an informal way. Actually, this is also an informal way, but it should be clear what I'm talking about. Now let's compute the probability of AI. Okay. Now the first row is I. So sorry, the first row results in I. I don't care about the second row. So what are the possible outcomes? I1, I2, I3, and I4. So 4 out of 16 outcomes, right? Satisfied A1, AI. All right. And I don't want to belabor the point, but BJ is also 1/4 by complete symmetry. So we see that probability of AI intersect BJ is exactly probability of AI times probability of BJ, which implies that AI is independent of BJ for every IJ in 1 to 4. Finish. So here is a calculation, the formal calculation to show that the first row being something is independent of the second row being something. Is that clear? Any questions? This is the easy thing. 瑞学, right? 要学. Oh, okay, later you write it down. Agree? Okay, no typo? Very good. Okay, now let's consider, this is part A. Part B. Now, A is the event that the first row is 1. And B is the event that the sum of rows is 5. Oh my goodness. So this is not so obvious, highly not obvious whether it's independent or not. Now, you might think that, oh, the first row is 1, right? So, I mean, there could be some independence of the sum of the rows being 5. There could be some dependence because you know that the first row is 1. So you could give you some idea that the sum of the 2 rows is 5. So you need something that, you know, is happening. But, you know, the first time I looked at this, I thought it was very difficult. Intuition. The intuition is difficult. But actually, it's not so difficult because if the first row is 1 and you want the sum of the 2 rows, so the sum of the 2 rows is 5, the second row must be 4. Okay? Then you have to compute what is the chance that the sum of the 2 rows is 5. And we can list down all the possibilities. And we can see that actually these 2 events are independent. So let's do a calculation. claim is that A is independent of B. So in order to do this claim, we have to consider the intersection. So here, what is the meaning of the intersection? The first row is 1 and the sum is 5. So the first row is 1 and second row is 4. So this is the same as the probability that of the outcome is actually, sorry, this is ordered pair, 1, 4. And this is one outcome out of 16. Right? Okay. So hopefully everyone can follow this calculation. Can you follow this calculation? Right? The first row is 1, the sum must be 5. So the second row is 4. I skipped one step here, okay? Because this guy here is 5 and both of them must hold, so the second row must be 4. All right? Because both of them are in effect. Both of them must be active. Can you see here? Right. Cool. So what is the probability of A? Can anyone tell me? Very good, 1/4. We have already done this calculation above. All right. Probability of B is actually not so easy. Okay. Now, what is the probability that the two rows, the sum of the two rows is 5? So we have to list out all the possibilities. How do you get 5? All right. 1, 4 is 5. 2, 3, you get 5. The order matters, 3, 2, and this is 4, 1. All right. Note that 2, 3 and 3, 2 are not the same. So here I wrote 3 first, then I wrote 2. Here I wrote 2 first, then I wrote 3. Okay, so they are different. Now, here there are 4 outcomes out of a total of 16. So this is 4 by 16. Agree? 4 by 16. So now you can verify that P of A intersect B. This is equal to how much? Is equal to 1 over 16. Then we ask ourselves the question, is it equal to PA, PB? Now this is 1 over 4 times 4 out of 16. So that's exactly 1 over 16. And so this is true. And so A and B are independent, which is what we sought to prove or sought to calculate. All right. Is this clear? Everyone can, yes, David, what is your question? Yeah, intuitively, the first time you read this question in the book, you would think that B somehow depends on A. But it turns out, if we adhere to the definition of independence that I wrote down properly in this box here, or equivalently in the double dagger here, this is something we always check, then the two events are mathematically independent, even though they may not be intuitively independent according to our intuitive understanding. So we need to follow the mathematical definition and calculate all these quantities. The book also says that this is not intuitive. Or they have some nice phrasing there, okay? So we need to calculate these properly. Okay, so now let's look at something that is indeed not independent. So A is the event that the max of 2 rows is 2. And B is the minimum of 2 rows is 2. Now, so intuitively, if I know that B is true, does it influence my knowledge of the veracity of A? The fact that A is correct or incorrect. So if I know that B is true, all right, then the maximum cannot be 1. Because if I know that B is true, the minimum is 2. So the 2 dice, you have already eliminated the possibility that the maximum is 1. Now, A says the maximum is 2. So if you know that the maximum cannot be 1, it somehow influences you to change your overall opinion of what the maximum is. even though this 1 is not this 2. But if you know that the minimum is 2, you know that neither of the dice can be 1. Okay, so the maximum cannot be 1. So that somehow has some influence on your belief about whether the maximum is 2 or not. And we will try to again make this precise by calculating the probability of the intersection. All right. So what is the probability of the intersection? Well, this says that, let's write this in English. The maximum and minimum of the 2 rows are equal to 2. Okay, they are all equal to 2 because we have considered the intersection. So if the maximum and the minimum are equal to 2, both of them must be equal to 2. No choice. Correct? All right, so the probability that this happens, because it's 1 out of 16 possible outcomes, is 1 out of 16. Agree? Agree? Do you want me to go through this calculation? The maximum and the minimum are both 2. That means that both the tosses must be exactly 2. So this means basically that the first toss and second toss are 2. The outcome is 2. Okay. So now let's compute the individual probabilities, which is a probability of A and probability of B. Okay, so let's calculate this. Now, what is the probability of A? The maximum of the 2 rows is 2. So what are the possible outcomes? All right, the maximum is 2. So you can have 1, 2, 2, 1, and 2, 2. So only in these outcomes, the maximum is 2. Note that, fellow, 1, 1 is not outcome. It's not a legitimate outcome. Because here, what's the maximum? The maximum is 1. It is not 2. Understand? So these are the only possibilities. So this is how much? 3 out of 16. All right, and now let's calculate probability of B. Well, the minimum of the 2 rows is 2. That is the probability of B. So let's just remind ourselves of this event. So that the probability of the minimum of 2 rows is 2. Okay, so what are the possible outcomes? So we are just going to list. Okay, 2, 2. 2, 3, 3, 2, 2, 4, and 4, 2. If we do things systematically, we are good. Can you see? So these 5 possibilities are the only possibilities such that the minimum is 2. Other possibilities are all irrelevant because the minimum is not 2. Okay, and so here you have 5 possibilities out of 16. So now we have to ask ourselves a question. If I ask you whether it is in the events A and B are independent, you have to do this check. All right, you have to do this checking. A and B, is it equal to the product of probability of A multiplied by probability of B? So on the left-hand side, this is how much? We have already calculated 1 out of 16. And on the right-hand side, this is how much? 3 over 16 times 5 over 16. Which is 15 out of 256, which is not 1 out of 16. So it is not equal. So this implies that A and B are not independent. Now, not independent, there's another word for it, it's dependent. Okay. Right. Does anyone have any questions on this calculation? Or you can don't copy, it's all fine because it's all in the book, and I will also upload these handwritten notes, which I hope are readable. Any questions? It's all understandable, right? So the punchline is, okay, the punchline or the advice is when we ask whether 2 events is independent, to check if A and B are independent, check if the following equality holds. Which is probability of A intersect B is equal to probability of A, probability of B. So you just need to check this. It's usually easier to check this than to check the conditional versions. You can also check this. You can also check that. You can also check these two. But these are harder in general. You have to do a little bit more work. You have to do one more step of division. Okay, so I suggest you check this easier. Okay, but you can check whatever you want. This is advice. Is this clear? Do I have to repeat myself? How about the people in Zoom? Is this clear? I don't have to go very fast. We have 20 friends in Zoom. All right. I will call on the Zoom people to answer questions maybe later on. Right. We'll talk for another 20 minutes and then we'll have a short break. All right. So I have already talked about the notion of independence. Independence means this or this or this, all these are equivalent. And we have done an example to check whether some events are independent or not. So there are more examples in the book I will not go through. Now, a more difficult concept is called conditional independence. Now, instead of talking about two events, okay, we have to fix three events, A, B, C, that are subsets of the sample space, omega. And we say the following. We say that events A and B are conditionally independent given another event C if the following holds: probability of A intersect B given C is equal to probability of A given C, probability of B given C. Now, the first time you look at this, it is a bit complicated, but let me just provide a remark. If actually C is the full set, okay, is a full set, that means C is trivial, it's everything, you're given everything, you have no additional new knowledge, then conditional independence reduces or reverts to just pure independence. And the reason is because the equation star reduces to P of A intersect B equals to P of A, P of B. And the reason for this is because you take any set, any event A, and you condition on everything, all right, you should know that this is P of A. Okay? And the reason why this is true, let me just do a calculation, is because we can just go back to the formula A intersect the full set divided by probability of the full set. Now, if you have A here and the full set is here, the sample space is here, the intersection is nothing but A. A intersect everything is A. So this reverts to PA. And the probability of full set is 1. So this is PA. So here, if we take C to be omega, and we put C equal to omega here, then we can drop the conditioning and we revert to this simple equation of independence. Is that clear? So this is the definition of conditional independence. All right, but we can revert to conditional just pure independence by taking C to be everything. Now, alternatively, we can consider the left-hand side of equation star, and that is probability of A intersect B given C. Now we are just going to use Bayes' rule, which is probability of A intersect B intersect C. So here we are treating this one as one big event, and now we are using the formula for conditional probability. And in conditional probability, you take this event at the beginning here, before the condition, and you take its intersection with C. So you have the full intersection, and you are dividing by the probability of what you're conditioning on. Now, but the above here, by the so-called multiplication rule that we talked about last time, multiplication rule, and I don't have time to review it this time. This is PC, P of B given C, and P of A given B intersects C, divided by PC. Now, so assuming this is positive, we have that this is probability of B given C, probability of A given B intersects C. Okay, so the point here is the following. The point here is the following, and we have probability of A given B intersects C is nothing but probability of A given C. So why is that so? Because you see here, this is equal to, let me see, because by conditional independence, this is equal to probability of A given C, probability of B given C. And after this sequence of manipulations, we can cancel this. And so what we are left with is this guy here is equal to this guy there. Okay. Now, so this is very much like pure independence, because if I am allowed to drop the C, what do I have? It's probability of A equals to probability of A given B. That means B gives us no information about A. Okay. Now, qualitatively speaking, what this tells us is that given C occurred, the additional knowledge that B occurred does not alter the probability of A. Okay, so what this is saying is that given C occurred, so on both sides, C occurred. All right. The additional knowledge that B occurred, which means this guy here, does not alter the probability of A. That means this stays the same. All right. Here is you only know C occurred. Here you know both B and C occurred, but condition on you knowing C occurred, whether or not you know B occurred is immaterial in your trying to understand the probability of A. Now, this is a bit of a difficult thing at the very beginning. I took a few years to understand this, but it comes very natural. All right, it comes very natural when I draw when we give an example in real life. Okay, so let me come up with a real life example now. A is your health at age 3. B is your health at age 1. C is your health at age 2. Okay, this example I'm coming on the fly right now. Now, suppose a doctor is interested to know your health at age 3, whether you're healthy or not. And he knows your health at age 2. So C is what we condition on throughout. Okay, he knows your health at age 2. So now 2 is closer to 3 than 1. So all the information about you is already summarized in your health at age 2. He does not need to know what is your health at age 1. All right. So the information at the very early stage of your life is immaterial because I just need to know what your health status at age 2. This is one example of conditional independence. This is not in the book. I come up with it now. Okay. So now this is very fictitious, okay? Because now if I want to know your true history, then actually I need to know what is your health status at age 1. But fictitiously, you can imagine that if a doctor knows everything about you at age 2, he doesn't really need to know about age 1. All right, but you can conceive of this scenario that, okay, all the information about yourself is already summarized in age 2. If I want to say something about your health, or I want to learn something about your health in age 3, I don't need to go back to age 1. All right, so this is my fictitious example, artificial example. This is called, I teach a higher level probability class. This is called Markov chain. All right, but here I simplify it for you. All right, I don't know whether this is convincing or not, but never mind. We don't need to be very convincing, okay? But let us try to do some examples to see whether things are conditionally independent or not. So let us do one example and then we'll continue with another example after the break. This is a simple example. We have 3 events, okay? Toss a coin 2 times. And this is a 2-faced coin, okay? Heads or tails. So H1 is the event that the first toss is heads. This is an event, and H2 is another event. Second toss is heads. And the third event of interest is the 2 tosses are different. Okay, so this D here stands for different. Okay, that's the easy way of thinking about it. So I just want to summarize this, my example. Okay, it's not the book's example, that if condition on C, A, and B are independent. And this is the way you write it. Okay. Okay, so this is an example. All right, let's see whether let's see what are the independence relationships. Now, here, this example, the moral of the story of this example is the following. H1 is independent of H2. We will try to show this or argue this, or you can see by common sense, right? H1 and H2 are indeed independent, but H1 and H2 are going to be shown to be not conditionally independent given D. Okay, so we have this relationship and also this relationship. So we would like to do some simple calculations to show this. All right. So basically, the moral of the story is that you can have independence, but this independence can be completely violated if you are given another event. And this is a very simple example that illustrates this. Now, so let us do a calculation. Probability of, say, H1 and H2, okay? Because the 2 tosses are themselves independent, this is clear that this is, so this is the probability of the 2 tosses are heads. So this is probability of, say, heads. But this is one outcome out of 4 outcomes. This is 1/4. All right. But probability of H1, that is nothing but probability of heads, is half. Probability of second one being heads is half. So we have that the probability of H1 intersect H2 is equal to probability of H1, H2. And they are indeed independent, marginally. They are indeed independent. So now let's check the second statement. Condition on them being different, can they be, the 2 sources, are they heads or not? Okay. So let's see the following, okay. Now, here the conclusion is that H1 is independent of H2. Now, let's see. Probability of H1 intersect H2 given D. Okay, let me write some English first. Right. Now, we check whether H1 and H2 are conditionally independent given D. In order to check this, we have to check this relationship, whether this relationship holds true. So let's calculate all 3 things. Let's calculate all 3 probabilities, okay? So probability of H1 and H2 given D. What is the meaning? What is the meaning? Well, the English meaning is that the 2 tosses are heads. Condition on 2 tosses are different. So what is the probability here? You live in the world where the 2 sources are different. Very good. 0. Okay. Now, you're not done yet, okay? You're not done yet because you have to calculate these 2 things. So you have to show that these 2 things are positive. The positive thing cannot be equal to 0. All right. So you want to show this we have already calculated is 0. So now we are calculating these 2 things. But we only need to calculate one of them by symmetry. Okay. So let's calculate probability of heads given D. Slowly, let's calculate this, okay? Now, we have a lot of experience doing this by now, hopefully. So you use the formula for conditional probabilities. So this is H1 and D divided by probability of different. Okay, cool. What is the meaning of the top? The meaning of top is the first toss is heads and the two tosses are different. So the second toss must be tails divided by, well, probability different. But probability different, there are only two choices, heads, tails, and tails, heads. Right? This is the probability that they are different. Okay, so this can be summarized as probability of heads, tails divided by probability of heads, tails plus probability of tail, heads. Now this is nothing but a quarter divided by a quarter plus a quarter, which is how much? 1/2. Can everyone follow my calculation? Can everyone follow my calculation? Okay, Oliver, can you follow my calculation? No. Okay, I know you cannot. So let me go through this one more time. So in order to check whether H1 and H2 are conditionally independent given D, we have to check this equation whether it is true or not. Okay, so listen up, right? So let us compute this thing on the left-hand side. This thing on the left-hand side, what is the meaning? The meaning is that the two tosses are heads because H1 intersect H2. That means the first toss is head and the second toss is head. All right. What are we conditioning on? Which planet are we living on? We are living on the planet in which the two tosses are different. So if the two tosses are different, can the two tosses both be head? Cannot be. Zero. Perfect. So you understand half. Now this half is a little bit difficult. Probability of head, the first one being head, given that they are different. Okay. The two are different. What is the chance that the first one is head? So by using the standard formula, we have intersection on top and what you condition on bottom. Okay, this is the rule. What is the meaning of the top? The first toss is head because we take this into account and the two tosses are different. I didn't write that down. But if the first toss is head and the two tosses are different, the second toss must be a tail. Okay, so that is probability heads, tail. What is the chance that you get head, tail in this order in two tosses, Oliver? Head and tail in two tosses in this order. Yes, 1/4, and that is what I did here. I did a bit fast, okay? The bottom here is the probability that they are different. What are the outcomes that they are different? Heads, tails, and tail, heads, right? So Oliver has already said that heads, tails is 1/4. By complete symmetry, probability of tail, heads is also 1/4. So this number here is 1/2. I explained this to you, right? Okay. So by complete symmetry, H2 given D is also 1/2. I'm not going to do this. By complete symmetry. So the left-hand side is equal to 0. The left-hand side of, say, this star is 0. But the right-hand side is 1/2 times 1/2, which is 1/4, and certainly not 0. That means that H1 and H2 are not conditionally independent given that they are different. Can you see this calculation now? Do you understand this calculation? All right. How about Long Dengjie in the Zoom? Do you understand this calculation? Yes, very good. So now let's take a 8-minute break. We come back at 5 past the hour. Okay, 3:05, and then we'll talk about one more example of this. Okay, if you can figure out how to do it, I'm happy to do it. Because this.
We're gonna have to push buttons. Yeah, there we go.
Okay. Yeah, let me know if you want whatever environment, okay? Because I'm not very good at technology.
Yeah, mentioned that, but it's group chat and stuff.
Okay. Since you are here, you could have just shouted it out.
I don't want to sound rude.
No need to be nice to me. Right, folks, let us resume. Let me do one more example, okay? See, we have very little theory, but we do a lot of examples, okay? So now, let us do another example on conditional independence. So now we have 2 coins. Okay, and these 2 coins are blue and red coins. So we have this coin that is blue coin. This is the blue coin. And the probability of heads of this blue coin is 0.99. And we have this red coin. And the probability of heads of this red coin is 0.01. Now, the story is as follows, and this is a very interesting story. Now we're going to select a coin, either the blue or the red, uniformly at random. Actually, let me do the following. Let me write this in a more precise way. Okay, so this is probability of heads given blue. All right, this is more mathematical. Probability of heads given red. Okay, now we're going to select a coin, the blue or the red, uniformly at random, and we're going to toss it twice. Okay, so now let this be the event that the blue coin was selected. So of course, the probability that the blue coin is selected, because I said uniformly at random, uniform, right? So this is 1/2. There are only 2 coins. The probability that you select the blue coin, there are the 2 coins inside an urn, all right? A probability theory, people like to use urn for some reason. So you pick a coin uniformly at random, you have a 50% chance of getting the blue coin, all right? And 50% chance of getting the red coin. All right, so now let's see the following. Let's see, now suppose you pick the blue coin. That is what you are conditioning on. What is the chance that both are heads? That's H1, H2. H1, H2 are defined above, are defined here. Okay. Now here, head, first toss is head, second toss is tails. So these are the definitions. Sorry, I should put the definitions before the calculation, but you can see everything here. Now, once you pick a coin, you're going to toss the coin uniform. You're going to toss the coin 2 times, and these 2 tosses are definitely independent. Okay, and that is equal to 0.99 square, whatever it is. Because if you pick the blue coin, the chance that it is head is 0.99. And so you're going to plug 0.99 times 0.99 here. Okay, so that's a simple calculation. All right, now we want to ask ourselves the question. We're going to ask ourselves the question, is H1 independent of H2? All right, so is H1 independent of H2? Now, H1 and H2 are conditionally independent. Here, this implies H1 and H2 are conditionally independent if I know event B. Okay, that is definitely true. But is H1 independent of H2? So what do I have to check, folks? We have to check only one equation, which is probability of H1 intersect H2 is question mark H1, H2. We have to check this. Okay, so let's check this. All right. So let us check this slowly. Let's check probability of H1. Then probability of H2, we are not going to do. It's complete symmetry. All right. So now what do we use? Okay, what is difficult about this problem? Now, if I ask you, what's the chance that you threw a head in the first toss? The difficulty is you do not know which coin you pick, right? You do not know. You either pick the blue or the red. So the natural thing to do is to condition, all right? So this is probability. Use the law of total probability. B, you pick the blue coin, probability of H1 given B. So here is you are using the law of total probability, B complement H1 given B complement. And B complement means red, okay? So the probability of B is 1/2. Now, what is the chance that you threw a head given that you pick the blue ball or blue coin? Is 0.99 plus half times 0.01. All right. Now, the reason why this is half is because you pick the red coin with probability half. And what's the chance that it turns out heads? Well, you use this information. Now, from here, you see that this is half. All right. Similarly, and I'm not going to belabor the point, this is also half. So we have to check whether this is 1/4 or not. The joint, whether the probability of the intersection is 1/4. All right, we have to check whether the probability of the intersection is 1/4. Okay, so let's check that. So the probability of H1 intersect H2. Now, what is the difficulty here? The difficulty here again, now what is the event of interest? What are we interested in? We're interested in the event that the two tosses are both heads. This is the English meaning. Both tosses are heads. Okay, now this is difficult because you do not know which coin you picked. If you knew that you picked the blue coin, oh, it's very easy to calculate the probability. Now, if you pick the red coin, it's also easy to calculate the probability because you have all this information. But now you are left in the dark because you do not know which coin you picked. So the natural thing to do would be to condition. H1 intersect H2, condition on you. Wow, you picked the blue coin, you knew that. The probability you picked the blue coin plus H1 and H2, given you didn't pick the blue coin, you picked the red one, probability BC. Understand? This is an application of the law of total probability. B and B complement form a partition of the sample space, and B and B complement are disjoint. So here, what do we have? Now here, what is the meaning? We pick the blue ball or blue coin, and both turn out to be heads. All right? So that is, okay, 0.99 times 0.99. Now, probability of blue coin is 1/2, so we keep it here. Now, what is the meaning of this? This is, well, we pick the red coin and both turn out to be heads. Oh, you need to be very lucky here. Because to get one heads, it is 1% chance. To get two heads, it is 1% chance squared. And you have a half here, all right? Now, this one here is close to 1/2. It doesn't matter what it is, but it's kind of close to 1/2. This is negligible, and this is close to 1. So this is close to 1/2. All right, I don't need to press a calculator. Can you see that it's close to 1/2 from the numbers? And so this number here that we have is close to 1/2, which is clearly not 1/4. All right, so now you have the situation that H1 and H2 are conditionally independent given B, but from here, H1 is not independent of H2. Now, why is this so? Is there any intuitive reason? Now, notice the following. We can equivalently check the following. We can equivalent check this to check whether things are independent. We can equivalently check this condition, right? This is equivalent. If this is equal, right, then we are also, H1 is also independent of H2. Maybe it's better to flip this around. H1 here. Okay. This is also, you can check this. Okay, you can check this if you want, because this is equivalent to what we checked, which is the product. And I say that this is usually simpler, but equivalently you do this. Now, this is not true just by looking at the numbers. Why? Now, here is what I know. Oh, this is what I know. What is the meaning of what I know? H1 is true. That means I know that the first coin is head. I know that the first coin turned out head. Now, that will bias my belief that the coin that I actually picked is the blue coin. because the chance of the blue coin being hit is super high. So let me write some English here. If I know that the first coin turned out to be hit, then there is a high chance that the coin I picked is blue. And consequently, there's a high chance that the second toss will be hit. Okay, so sorry about this very bad English, bad handwriting, but I think you know what I'm trying to say here. If I know that the first toss is hit, then there's a very high chance that I picked it from the blue coin because, you know, this is super high compared to that. So there's a high chance that the coin I picked is actually blue. Now, consequently, there's a very high chance that the second toss is also hit. So this biases my belief. If I know this, it biases my belief that the second toss is hit compared to the scenario that I do not know that the first toss is hit. This is completely, you know, independent. And this is equal to half. So a priori, this is half. But if I know that the first toss is hit, what is the chance that the second toss is hit? You can go and calculate this homework. All right, and this will be very high. This is not going to be half, close to 1. Go and calculate this. Okay, it's going to be very close to 1. Now, you don't have to understand my intuitive explanation if it is not clear. You have to understand my mathematical calculation above. The intuitive explanation will take you some time to digest. This intuitive explanation. You don't have to understand it, you can go back and deliberate. But what you need to know is how to do the mathematical calculation. Okay, how to use the law of total probability, etc., etc. This is using the law of total probability many times. Any questions? Now, these people, are they going to talk to me? All right. Oh, there are no questions from the audience. Okay, so this is some intuition. Now, in the textbook, there is a generalization to mutual independence. So I just want to quickly go through this, and I'm not going to talk about too many examples because we may not need to use this too much in the following, all right? So an extension is the following. An extension is, so if I have events, n events, say A1, A2, A3, okay, there's 3 events, independent. Now, previously, we only talked about independence of 2 events. If for all subsets of 1, 2, 3, the following hold, all right? So we have probability A1 intersect A2 is equal to, so you need to have the pairwise ones. A3 equals to probability A1, probability A3, and probability A2 intersect A3 is probability A2, A3. These are called pairwise independences. Independence. And you need the triple wise. A1, A2, A3. If you have all these, we say that events A1, A2, A3 are independent. That is the generalization of 2 events being independent to 3 events being independent. And you can generalize this to n events in being independent. And just some remark, and there are many counter examples that are present in the book. Now, pairwise independence doesn't imply independence in the sense of having all the relations hold. So you could have these 3 satisfied and the last one not satisfied. Okay, and if we call this star, that means triple wise independence alone doesn't guarantee pairwise independence. Okay, so there are some counter examples in the book, but oh, David has no questions. Good. So there are some counter examples in the book that illustrate this, and I'm not going to go through that. All right, because we may not have to use this many events being independent too much in this class. Okay, so in the last 20, 30 minutes or so, I want to go through the final concept in chapter 1, all right, which is counting. Actually, counting is the most difficult thing that I've encountered, you know, in whole probability, because you can be very creative with questions. Okay. Right. So these counting questions can be super tricky. All right. So let's say that a process has a total of R, integer R stages. Okay. And there are N1 possible results in the first stage. Now, for each result in the first stage, there are N2 results in the second stage. And more generally, you have the following scenario. So this is the first stage. Say you have N1 equals to 3 possibilities. And for the second stage, you have, say, for each possible result in the first stage, you have 4 possibilities in the second stage. Okay, so here N2 is equal to 4. And for each one of the results in the second stage, you have 5 possibilities in the third stage. 1, 2, 3, 4, 5. So that is N3 is equal to 5. So how many possibilities are there altogether? Right? The number of possible results or for the R stage process is the product N1, N2, N3, all the way up to NR. Hopefully you kind of understand this. All right. Now, this picture is not very well drawn because I have to insert all these 5 splittings for each one of the branches in the second layer of the tree, but I am not going to do that. Okay, so this is a theorem. It's a logical thing, but it's kind of important. And so we'll illustrate this with an example. Okay, so here we are interested in the number of telephone numbers. So, you know, there are many scams. So we need to know the number of telephone numbers. So here, each telephone number has 7 digits. I guess this was before you were born. When I was born, the telephone numbers in Singapore had 7 digits. Sequence. 7-digit sequence. So here the rule is that the first digit must be different from 0 or 1. Okay, so the first digit cannot be 0 or 1. Now, and the total number of digits is 7. How many phone numbers are there? How many distinct phone numbers are there? So this, hopefully, by logic, right? You know what's happening here. So there are 7 digits altogether. 1, 2, 3, 4, 5, 6, 7. All right. Now, in the first bucket here, what are the possible numbers that can go inside? 2 to 9. So let me use this MATLAB notation, 2.9. That means all the numbers from 2 to 9. You cannot have 0 or 1. So here you have 8 possibilities. Right? Agree? Because the rule says that you cannot have 0 or 1 in the first bucket. Now, how about the second bucket? How many numbers can you have? 10, right? I think you can have 0 all the way to 9. 10 possibilities. Here, 0 to 9. Same thing, or ditto, here, 0 to 9. Right? So here you have 10 all the way 10. How many possibilities are there? You take the product of these numbers, you have 8 times 10 to the power 6. Understand? That's the application of the above rule. Very obvious, right? Oliver, understand? So here we have a phone number. We have a bunch of phone numbers. How many phone numbers can we form? The first bucket, the first digit cannot be 0 or 1. So it can be 2, 3, 4, 5, all the way down to 9. But the rest are unrestricted. Okay, the rest you can have any numbers from 0 to 9. 0 is included. Right? 0 to 9 got how many numbers? 10, right? So 8 times 10 to the power of 6. Because here there are 6 buckets here. All right, so you have 10 to the power of 6, and the 8 comes from here. Because the first 2 numbers cannot be 0 or 1. So 2 to 9 got 2 to 9, how many numbers? 2, 3, 4, 5, 6, 7, 8, 9. 8. Got it? Yeah. These numbers are enough for us to use our fingers to count. David, this is neither permutation nor combination. We are getting there soon. This is just counting. What does the book call this? Exhaustive counting, right? I'm getting to permutation soon. Okay. All right. So people often get confused by permutations and combinations. So do I. Always get confused. But we don't have to get confused if we know what we are doing. All right. We know logic. We don't follow rules. At least I don't follow rules. So now let me talk about K permutations. You have n distinct objects. And we have a number K that is not more than n. So K is between n and 1. So the question is, how many ways can we pick the K objects and arrange them in a sequence? Okay, so this English sentence has 2 phrases to it. Can we pick the K objects? Sorry. Can we pick the K objects here? There's one phrase. And arrange them. I meant to use a different color. And arrange them in a sequence. So the order actually matters. So here, how many students are there? Say 20. Now I'm going to pick 5 people here, and I'm going to arrange you in this bucket. First person, second person, third person, fourth person, fifth person. How many combinations, how many permutations can I have here? The order of the person actually matters. Okay, so the idea is as follows. You have n objects all together, and you want to put them, so you have n objects, and you want to put them into K buckets. So here are the K buckets. K objects in a sequence. So it's logical, right? You think about it. How many ways, say K is equal to 1. You're just picking one person and putting him or her in a position. How many ways are there to pick this person? One person only. There's one slot here, one seat here. Out of the n people, I choose one person. How many ways are there? How many ways are there of choosing? Someone help me. What is a bucket? Okay, a bucket is a bin, like a bin you throw people inside. So there's one bin here. I want to throw one person inside. How many ways are there of choosing one person? There are n people in this room. N, right? So if I have one bucket, here one bucket, one place for you to sit down, there are n ways to choose. N ways here, right? Now I've already chosen that one person and I put him or her into this bucket. Now I go on to the next bucket. How many remaining people do I have to choose from? Can I choose from? So I chose you already, you sit here. Okay, you sit here. Now there are n-1 people remaining. I want to choose among these n-1 people to sit in the second bucket. How many choices do I have? n-1. You agree? You have already, one person has already sat down here. The second person sits down here. So there are only n-1 choices here. Right? And then now I go to the third bucket. I have already chosen you 2 guys sit down here. So there are n-2 people remaining. So third bucket is here. How many more choices? How many choices do I have to put one person out of the n minus 2 people here? N minus 2, right? Okay, n minus 2, all the way up to n minus k plus 1, because there are k here altogether. So how many ways can we pick k objects and arrange them in a sequence? The order matters. So the answer here is n times n minus 1 times n minus 2 all the way up to n minus k plus 1. There are a total of k numbers here. Please note that there are k numbers here because we start with index 0. Okay, so there are k numbers here. You go and count. All right, so this can be expressed in a slightly different way. N times n minus 1 times n minus 2 all the way up to n minus k plus 1, n minus k all the way up to 2 times 1, divided by, let me move this down a little. Okay, divided by what? N minus k minus 1 dot 2 times 1. The reason is because all these things can cancel. You can cancel this. This can be cancelled with this. All right, so I recover this. The reason why we do this, we write these additional things, is because we can use the factorial notation, n factorial over n minus k factorial. And n factorial is equal to n times n minus 1 times n minus 2 dot times 3 times 2 times 1. Okay, so that's the meaning of factorial. Okay, so this is the number of ways we can choose k objects in a sequence. In a sequence is super important. The order matters. So this is often given a name. All right, this number here is often given a name. Depending on where you come from, right? If you come from say China, right, then they write like this, MPK. Maybe, yeah. So I think this is some way that people write, but we will stick to this notation in the book, because there's the notion of combination. Some people write this NCR, all right, later on. But now let's illustrate this with an example. I know this can be a bit abstract and very difficult. How many words can we form? Words that consist. How many words consist of 4 distinct letters? Now, notice that words, in words, the order matters. The order matters, right? So, for example, DOG is not the same as ODG, all right? The order matters. Okay, so how many words can you form with 4 distinct letters? Well, so you have 4 distinct letters, you have 4 buckets to put your words. Here you have 26 ways. You can choose A to Z. Now, after you have chosen A to Z, say you chose J, you only have 25 letters to choose from because it must be distinct. So you have 25 here. Okay, say you chose J. So you cannot choose J again. All right, 24 here and 23 here. So the total number of ways you can choose, you can choose 4 distinct letters is 26 factorial over 26 minus 4 factorial, which is 26 factorial over 22 factorial, which is exactly the product of these numbers here. Times, okay, which is this. Does that make sense? So we are interested in choosing, but placing the things that we chose in a particular sequence. The order matters. So, yeah, we'll illustrate this using another example shortly. Okay. So this is a simple example. You can look at some other examples in the book. All right. So here, permutation order super matters. Okay. There's one more thing you need to know. And that's combinations. And it's different from permutations. Combinations. Okay. Now, here, order does not matter. What do we mean? Now, here's an example. There are n people all together. We want to form a committee of k people. And of course, if you form a committee from n people, right, the k must be between 1 to n. You can form a committee with one person. That means you are the dictator, all right? But usually we don't have a committee with one person, all right? We have a committee of 3 people, for example. All right, but the committee of 3 people, right? The order does not matter. So, for example, David and Oliver and myself, we are in one committee. We all work together. No one is the boss. All right, so we are all a committee, a set, okay, of people, right? So order does not matter. I've already said this. And I want to emphasize this. Here, the order does not matter. All right. So let me illustrate this using yet another example. All right. So let us see the 2 permutations, the set of all 2 permutations of the letters A, B, C, D. What are the 2 permutations? The order now matters because I'm talking about permutations. So AB is 1, BA, AC, CA. These are all the permutations of 2 out of 4 letters. BC, CB, BD, DB, CD, and DC. You can see that DC is different from CD. The order matters in permutations. But in combinations, okay, in particular, 2 combinations from the alphabet, A, B, C, D, what are they? Okay, so AB, okay, AB is 1 combination. So these are the 2 people in the committee. Whether it's AB or BA, they are all still the same committee, right? Now then we have AC, so the order does not matter. AD, these are all different committees because even though they have the same A, the other person is different. Okay, so the order here does not matter. All right, and BC, BD, and CD. All right. So as you can see, here's the difference between permutations and combinations. In combinations, the order does not matter. All right. In permutations, the order matters. Look at this. These 2 order matters, and here we have dropped the BA. Drop the BA. Okay, because BA is the same as AB in the theory of combinations. Okay. So notice the following. How many combinations are there if I have n objects and I desire to form a committee of k objects? So from permutations, there are more permutations than combinations. That's the first thing you notice. Combinations, we notice that each combination is associated to k factorial duplicate k permutations. So the number of combinations is exactly the number of permutations, which is npk divided by k factorial. Let me write this properly. The number of combinations is exactly this. Now, let's look at this example here. This is one combination, but it's associated to these permutations. How many permutations are they associated to? 2 factorial. 2 factorial is 2 times 1 is exactly 2. So this one is associated to this. They are in the same group. Okay. So in order to get from the number of permutations, which we have already figured out, to the number of combinations, we take the number of permutations divided by k factorial. K factorial is the generalization of this 2 factorial. 2 factorial is 2. But this can be written out in some of a closed form expression divided by n minus k factorial, Because we know that npk, because we know that NPK is equal to n factorial over n minus k factorial. And this is usually given some symbol. Now, in China, it's given this symbol. In the book, it is written n choose k like that. Okay, you will see everything. So this is read as n choose k, which is very suggestive because we are choosing k things out of n things without order. Okay, so the number of permutations is exactly this in green. But how to get from the number of permutations to the number of combinations? You see that there are repeats here. We want to throw away this because this is just a reordering of AB. Throw away. So for every group that has the same elements, right? We want to throw away the replicates. How many replicates are there? They're k factorial duplicate. So we just want one representative. So we know the total number of permutations is this. So how many combinations are there? We have the number of permutations divided by the number of duplicates. Here, the number of duplicates is 2 factorial. In general, it will be k factorial. But the number of permutations is n factorial, n minus k factorial. So we need to further divide by this. But this quantity here is given a name. It occurs so often. It's given the binomial coefficient name. Okay, this is also called binomial coefficient. Or n choose k, all right? Or nck, all right? You see all this. All around, you will see all this. Okay? Right, so let us try to do one example and to call it off, call off today. All right, what are the number of combinations of 2 out of 4 letters from the alphabet A, B, C, D? Well, we plug into the formula, all right? So this is our n and this is our k. So n choose k is equal to n factorial over n minus k, k factorial. So 4 factorial divided by 2 factorial times 2 factorial. Because 4 minus 2 is 2, okay? 4 minus 2 is 2, so we have this. It's 4 minus 2. Okay? Oh, here there's a factorial missing. Okay? So we have this 4 times 3 times 2 times 1. 2 factorial is just 2 times 1 times 2 times 1. So you have a lot of cancellations here. You can cancel this with this, and you can, this is 12 divided by 2, right? 12 divided by 2 is 6. All right, and we check this, how many we have here? If I listed all of them out properly, we have 6. Right? So by listing out or by using the formula, we get the same number of combinations. Next time, we will do one more. I don't know what's triangular number, David. What's a triangular number? Maybe. They are all elements of the Pascal triangle, if you wish. What is question mark, question mark, question mark? So I think the student there also does not know what's triangular number, but I think it's Pascal triangle. Yeah, it's all combinations are part of the Pascal triangle. You can go and Google it. So today we talked about independence, and we also talk about combinations, permutations, and so on. So there's a lot more we can say. I've only scratched the surface here, and I've only done the simplest examples. But next time, on Tuesday, we will start with a bit more difficult example for permutation and combinations. I don't want to do a very difficult example right now because it's already 2 hours. So I will wish you the very best in your enjoyment over the weekend. And okay, so okay. If you need help, we have office hours to help. I don't know where other classes have office hours or not. I don't know what it's called here in NUS. Okay. Yeah, I released the assignment because I allow you to do the easier question first. You can do the permutation. But I give you a lot of time until the end of the month, right? Oh, okay. Okay, anyway, I think it's easier if I give it to you sooner rather than later. No. I don't know how to satisfy all of you, but I'm trying my best, okay? Any questions, you can come down and ask me, and I'll have, if I can answer, I'll answer. If I cannot, I will Google it, okay? Take care. Bye-bye. Bye, people in the Zoom.